Space, the final frontier. These are the voyages of Yurtesh Sohal. His ongoing mission to speak to scientists and other very interesting people. Welcome everyone to the Frontier of Knowledge podcast. Today I'm going to be joined by Dr. Tessa Baker, who works in the Department of Physics at the University of Oxford. In today's conversation we're going to be talking about gravity, dark energy, dark matter, and gravitational waves. Now, strap in, hold on to your seats, and let's delve into the majestic void we call the universe. Yeah. Hi everyone. Welcome to the Frontier of Knowledge podcast. Today I'm joined by Tessa Baker. Tessa, if you want to introduce yourself, give us a bit of background on what you do, and just let the listeners know what you've been up to recently.
Okay, so I'm Tessa. Officially I'm a postdoctoral research fellow. It's my title. Mm-hmm. So essentially that means I'm a young scientist in that sort of region between PhD study. So I finished studying, I've got my qualifications, but obviously I'm not an established professor. I'm not a tenured academic. So you're a postdoc in that interim. And I work here in the Oxford University Department of Physics. And I belong to the sub-department of astrophysics, and I also have I belong to one of the colleges of Oxford University, All Souls College. I'm a cosmologist by trade. So what does that mean? Cosmology is a particular subfield within astrophysics, and it's to do with the study of the large-scale properties of the universe. So within astrophysics, we've got all kinds of questions going on. I've got colleagues who study planets, I've got colleagues who study stars and study galaxies. My piece of that is that I actually study the large-scale collections of those things. So we ask questions like, how did the universe begin? How did we get from that early beginning, something like a kind of Big Bang, a sort of, some kind of primordial fireball explosion, to us clearly sitting here on a nice calm planet, not in the middle of a fireball. How does that happen? And what happens in future? How fast is the universe expanding today? And in particular, my work focuses a lot on the laws of gravity. I'm trying to understand how gravity fits into that whole picture of the beginning and the subsequent expansion of the universe.
That is a pretty awesome job you have, I'm not gonna lie. That is, you're at the forefront of science, really. That's pretty amazing.
It's a dream job.
I can imagine.
It's a dream job.
Nice, that's awesome. So how did you get into this? Like, at what point did you think, I'm going to become an awesome scientist and study the universe and try and figure out the secrets of nature and basically do awesome things?
So it was probably somewhere towards the end of secondary school.
Okay.
I used to get the train to school every day, and I can't remember why now, but one day train was late or whatever, and I bought a copy of New Scientist from the newsstands, and I started reading New Scientist on the train every day. I read it religiously, cover to cover, and that really got me hooked. I mean, a lot of the stuff I was reading was very sensationalist and quite vague, and looking back on it, I can sort of see all the flaws in it. But at the time, some of those big headlines really grabbed me. Part of our universe is missing, and things like that. And there were also some great documentaries on TV at the time with, people just talking about dark matter and dark energy and all these big problems in cosmology. And I guess I realised I was very lucky that I sort of cottoned on to this whole field of research just about the right time in my life, that if I started making the right choices now, because I was just at the stage of choosing A-levels and things like that, I could actually, potentially, with no certainty, but I could at least try and actually work in this field and make a career out of it. This didn't just have to be a kind of hobby or something I read about on the train. If I did the right steps, I could actually potentially join one of these people working on this, be one of these people working on this fascinating area.
That's really cool. So basically you just motivate yourself to just one day, I'm going to do this, and you stuck to it.
Yeah, absolutely.
That's amazing. It's hard work and dedication right there.
It's hard work. It's been a lot of hard work. I mean, sort of started doing this when I was 17 or 18. I had to make those choices, and I'm 29 now. So it's been a lot of long time in the training.
That's awesome. It's really amazing. When I was growing up and stuff, I used to watch stuff on like Cosmos, the original series of Carl Sagan.
Yeah.
And the newer one with Neil deGrasse Tyson. That was amazing. That really hooked me back into it again. And I think generally, a lot of the time, like people like such as yourself and different scientists in physics and stuff need to be more kind of celebrated. I mean, this is kind of the work you're doing. I think is extremely fascinating, and without your kind of work, we wouldn't really have the knowledge of understanding of how things are working, which is great, really.
That's kind of you to say so.
That's good.
There's still a huge number of questions. So actually, one of the really, I think, fascinating things about cosmology is it's not just the state of the field. Even today is not just refining details. It's actually big pieces of the puzzle are missing. So you may have come across these words in popular media like dark matter, dark energy, and explain those things in detail if you like.
Of course, go right ahead.
Okay, fine. So there seems to be a big mismatch when we look out at the universe and we use astronomical observations. So we have telescopes that can sort of look at the properties of and positions of millions of galaxies and through various techniques work out how fast the universe is expanding. And there's a mismatch between what those observations imply about the contents of the universe and what we see with our telescopes. So, for example, how to put this? We count up all the galaxies we see, and we see a certain number of galaxies X. But the expansion rate of the universe seems to be telling us that there must be much more matter in the universe than is accounted for in all those galaxies. And not just one line of evidence, multiple lines of evidence seem to give us the same result over and over again. So we're led to the conclusion that there's a substantial fraction of the universe that exists in some form of matter or some form of energy. And when we go into the details, you sort of split it into these two kinds of things: dark matter and dark energy, which have to be different. But these things that are not ordinary atoms, like you and I, are made up of. And so we can't see them. They don't interact with electromagnetic waves, which basically means they don't emit light. They don't give off photons like
we do.
Exactly. The reason we see ordinary galaxies is because they've got stars shining in them throwing out photons. And whatever this new stuff is, it's not throwing out photons. We can't see it directly. We only infer its existence.
So I looked at some research and found that only 4% of the energy is actually 4% of the universe is only matter. 25 from dark matter, and the rest 70% is dark energy. And so do dark energy and dark matter interact with gravity then, as such? That's one of the ways you can detect that it's actually there.
Right, exactly that. So dark matter is perhaps the easiest one to understand. Certainly does interact gravitationally. So what we believe, the current picture is that you have a galaxy, and all the stars in the galaxy are made up of ordinary atoms and things. But sitting around that galaxy is what we call a halo of dark matter. So it's a giant container, if you like, for that galaxy. And the fact that matter is there influences things like how fast the galaxy is rotating, and it's basically the gravity of that dark matter has a direct influence.
So it's basically the invisible weight we can't really see, essentially.
Exactly. Invisible matter.
That's pretty cool.
Dark energy is a little bit different. So dark energy is a bit of a placeholder for our ignorance. Really.
Of course.
Right. So what we have observed through many lines of evidence, but particularly by looking at supernovae, so that's distant stars that are exploding, we can work out how fast the universe is expanding. And what we find, actually, really bizarrely, is that the expansion rate of the universe is speeding up.
So it's accelerating by a factor of of x, for example.
Yeah, well, okay, don't even need to think about factors, to be honest. The fact that it's accelerating is almost completely the opposite of what you'd naively predict.
Yeah.
If you just had a universe full of heavy stuff, matter, you'd expect it to expand, yes, but you'd expect that expansion to slow down.
And then come back again.
Maybe it'd expand forever and just kind of, at infinity tend to a stop.
Yep.
Maybe it would even collapse, and a big crunch scenario. And actually, the fact that it's speeding up is totally bizarre. So there are various kind of explanations on the table, but we're not sure which one's correct. The sort of standard explanation is to say that there's this thing we call the cosmological constant.
Okay.
So it's like saying that just a region of empty space has a certain amount of energy in it.
Okay.
Even if there's no matter or anything, just the vacuum of space has this kind of basic energy that you can't get rid of. And if you work out the maths, having that pure kind of basic energy there would actually cause the universe to speed up.
So essentially it's the space in between the galaxies, and all the other regular stuff we can see is expanding like a balloon, essentially, with the dots on the balloon. As you blow the balloon, it expands further and further.
Exactly right.
Okay. So the next question I'm going to ask you is a bit kind of bleak. So how do you think the universe will end, essentially?
Okay, well, so it kind of relates to what I was saying a moment ago. If the cosmological constant explanation for dark energy is true, then we can tell you what the universe will do. It will just carry on accelerating forever and ever, and it will basically eventually expand so much and so fast, and this is way into the future, billions and billions of years, that basically all the stars around us within our own galaxy will eventually recede so far away that we won't be able to see them.
So we'll truly be alone, essentially.
We will be alone. Literally, the stars in the sky will go out one by one, and we will just be sitting in a black, empty
void, essentially.
Universe, which would be atrocious. However, as I say, it's an open question, so there are other possible explanations for why the universe is speeding up. And if one of them were true, then things might work out differently.
So what other kind of theories are opposing to the one that you're talking about right now? What other explanations can...
Yeah, so this is something that is actually the bulk of my research to date. There is an idea that the laws of gravity we are applying to the universe might not be quite correct. So our standard theory of gravity is Einstein's theory of general relativity. It's basically what Albert Einstein is really famous for. Right? And when Einstein put forward his theory in 1915, it explained all sorts of puzzles in the data and works really well on the scale of our solar system, for example. So you look at the planets moving around the sun, Einstein's theory describes that beautifully. You can look at stars moving in a galaxy, so slightly bigger scales, and Einstein's theory works really well there too. But that doesn't necessarily mean that you can just take Einstein's theory and apply it to the universe as a whole on the very largest scales. That's a hypothesis that needs to be tested. So it's possible that maybe there might be corrections to Einstein's theory that only affect that really large distance scales of the universe. And then basically we have an extended theory of gravity.
Interesting. So it's just kind of adding to what was already been put forth.
Yeah. So no one's saying Einstein's wrong. It's only maybe, and this is the open question, there could have been things he couldn't have known about with the observations that were available at his time that actually changed the behaviour of gravity on large scales. And maybe if we can work out what that extended theory is, that will tell us why the universe is speeding up.
Wow. As I said before, I was watching a few lectures on general relativity, and I was looking at gravitational waves which were discovered recently. And I thought that was amazing. Watching or observing two black holes merging, and then you can see the fabric of space-time rippling, is just an absolute crazy, amazing thing to be able to observe. And I just wanted to get your thoughts on how long, what are the implications of this, and what does it actually mean in terms of what we can do now with that kind of information.
Right, exactly. So perhaps a little bit of background here is useful. So part and parcel of Einstein's theory is it tells us that space-time is this dynamic thing. Right?
Okay.
It can ripple and it can wave like waves on the ocean, and these waves, we've known about theoretically. We can sort of work them out in mathematics, and they've been predicted for 40 years or something.
Yep.
But we've never, until last year, been able to detect them directly.
Okay.
And the reason is they are very, very faint, these waves, so our detectors have never been good enough.
Okay.
They're only produced in really, really high energy events in the universe. So there are two things in the universe that can produce gravitational waves. One, as you say, is merging of black holes, and the second thing is the Big Bang itself.
Okay.
So the ones that were discovered last year were indeed from merging black holes, and so that means for the first time we've actually got a way of seeing, well, in inverted commas, seeing that event directly.
Yeah.
So the problem with black holes is that you can't see them, right? They don't let anything out. They don't let matter out. They don't let light out. So you can't actually sort of look at what they're doing. So the gravitational waves provide us with a way to work out what they're doing, and also just the fact that you can see space-time itself waving. I mean, it's just insane.
It's quite funny, quite ironic. It's just saying, "Hey, look at me, guys! I'm right over here. You can see me, and I'm real."
Well, it's been doing that forever, but we just haven't had the right detectors.
The most fascinating thing I found about that is that the two black holes merging happened at over 1.5 billion years ago, which I think is just absolutely amazing.
Yeah.
It just shows you the scale of how big the universe is, and there's so little we know. There's so much we need to know in this field, and 1.5 billion years is such a crazy number to think about.
Oh, absolutely, absolutely. And then
can't even comprehend it.
And this happens all the time in cosmology. The distances and the timescales are involved are so vast.
Wow,
and
amazing.
I mean, quite often what we do, obviously, to make things tractable for ourselves on a daily basis is we put stuff in funny units.
Yeah.
So we measure distances in terms of something called parsecs. We talk about megaparsecs, the universe. And so, if something happens at a few hundred megaparsecs, a few hundred, that's
not big.
That's a number I can deal with. That sounds like, going to the shops or something, right? And actually, when you put it into meters, it's such a staggeringly large number. You just can't grasp it. No. I don't think the human brain is capable of imagining the sizes involved.
It's quite true, actually. When you're trying to imagine, even if I said to you, try and imagine 10 elephants in your head, it'd be quite difficult to actually see them individually, yet alone billions, trillions, and all these different, huge scale numbers. There's something I've always actually wanted to ask someone in physics, actually. Well, on my computer, I have different images of this Hubble telescope. So I have different kind of nebulae. I have different kind of stars on there, looking at different galaxies. And one day I was sitting on my computer and I was wondering that if the space around us is a fabric, and a black hole is basically just a very strong gravitational force sucking everything inside of it, which causes the warping of space-time. Does that suggest that maybe perhaps, because information can never be destroyed in that sense, does that mean that information is then sent somewhere else? So it's going to sound a bit far-fetched, but I've always wondered, maybe perhaps there's different kind of dimensions towards where a black hole can send that information, perhaps?
Okay, so various things going on here. How to put this? Okay, first of all, what is a black hole? Well, fundamentally, a black hole is an object that contains at its centre something called a singularity. And a singularity is, almost by definition, a point where the laws of physics break down. Okay, it's sort of dramatic as that sounds. So we can do all sorts of calculations in general relativity, tell you all sorts of things about what happens to matter, to information, up until the moment it hits that singularity. Okay. And once it hits that singularity, we literally cannot use our equations anymore. So, this question of where does the information go is sort of a very difficult one to answer. Now, there are some very famous mathematical proofs in general relativity that say, or some theories that say, some of the information that goes into that black hole potentially can come out again in the form of something called Hawking radiation.
I have heard about that. Okay.
Right.
But if you want to, can we give a bit more detail for some of the listeners?
Well, I mean, maybe it's a slightly technical thing to go into, but essentially what is often imagined is so what happens when you have a box of empty space-time is that particles can randomly pop out of the vacuum and disappear again. So this is quantum mechanics at work.
That is amazing.
What it says is laws of quantum mechanics allow two particles to be spontaneously created as long as they only exist for a very short period of time, and then they crash back into each other and they annihilate and they disappear from the universe again. Okay. Now, what Hawking imagined was, imagine you have two photons, or two particles of light, that are created, and they happen to be created exactly on the event horizon of a black hole. And an event horizon marks the sort of boundary in space at which you can't escape from the black hole. So if you're outside the event horizon, you might be able to escape. If you're inside,
you're going to die.
You're going to die.
Crippling death.
And so Hawking imagined what happens if pair of particles get created and one they move in opposite directions and one goes into the event horizon and one goes out. So normally what the laws of quantum mechanics would say is that those things must annihilate again, but they can't now because one of them's fallen in. So what actually happens is the particle that has not fallen into the event horizon, instead of being what we call a virtual particle, so one of these things that only exists for a very finite time, becomes real, becomes a real photon, and is actually emitted from the black hole. This is called Hawking radiation. I should say this is all mathematical and theory, this is not something we can observe directly. And there's, again, a lot of theoretical work, which I believe is not 100% kind of settled or certain, but it's still an area of study, is where the information that is fallen into the black hole can be carried out again by these Hawking photons.
Wow.
But there's a lot of debate going on, actually, within the past couple of years. There's been a huge amount of debate about what exactly happens when stuff falls into a black hole. Is information destroyed forever? Is it preserved in the black hole forever? Or does it come back out again in Hawking radiation? And it's a really tough area to study because it requires all the laws of gravity at full strength and quantum mechanics in this curved space-time. And that's an area we really don't know much about.
So can we apply Einstein's theory of general relativity and gravity to quantum mechanics? Because that's something I heard that we can't really do yet, and I don't exactly understand why we can't do that.
Right, so this is the famous quest for quantum gravity. So we know that there are four fundamental forces in the universe. There's gravity, there's electromagnetism, and there are two called the weak and strong nuclear forces, which are basically to do with what goes on inside atoms. And we know how quantum mechanics, which is basically a theory of what happens on atomic scales, fits in with electromagnetism and the strong and the weak forces. And so it seems kind of natural to say quantum mechanics must fit in with gravity somehow as well. But all attempts to construct a unified theory of those two, quantum mechanics and gravity, have failed. And basically what happens in sort of very loose terms is the equations just predict infinities. You start applying your usual tools, tried and trusted tools of quantum field theory, everything you know that's been built on for decades, and you just get garbage out.
So it's basically just something that we can't quantify, really.
We clearly haven't got the right tools. Whatever we're doing, standard mathematics doesn't work. And so there's, some people think of it as the sort of holy grail of modern physics, is to come up with this unified theory. So if you've heard of string theory, which gets a lot of press, sometimes in things like the Big Bang theory and whatever, popular science media as well. String theory is one attempt to try and construct a theory of quantum gravity.
Wow.
And it's the only sort of half decent attempt we've got at the moment. Now, that doesn't mean it's right or it's wrong. It's just one attempt. But these theories, these unified theories, are so hard to build. There aren't many other contenders around at the moment. So that's why string theory is at least a hot topic, whether it turns out to be right or wrong.
I found that really interesting, and I was actually looking into some science of the string theory and how certain strings essentially vibrate at certain frequencies, which produce certain quarks and different kind of particles. And so, can you give a bit of background on string theory and where it came from and how it can be applied to physics and what that basically means, really?
Okay, so the disclaimer here is that I'm not a string theorist most of my time, so obviously I know the basics. So I forget who it was now. I'm sorry.
So you have to
read a history of string theory. But the basic idea was put forward. Someone started with a toy model of what if at the most fundamental level of space-time. So when you go down below atoms, as you know, you get protons and neutrons. As you go below them, you get quarks, which you already mentioned. And what if actually all fundamental particles, like quarks and electrons and things, are vibrations of a fundamental object, a string? And there are various reasons why having a string, so something that's extended in one dimension, works very nicely. So you can think of different vibrations of this thing, different wavinesses, if you like, as giving rise to all the different fundamental particles, in the same way that a violin string vibrating at different frequencies gives rise to different notes. And there was a huge amount of mathematics that needed to be worked out for string theory, which was developed over sort of decades in the late 20th century. One interesting feature that comes out of string theory is that for things to really work, for the mathematics to work, and for kind of all the beauty of the theory to fall into place, it needs the universe to exist in more dimensions than the ones we observe.
Interesting. Okay, so my next question is, I have looked at some videos looking at different dimensions and looking obviously at the 1, 2 and 3, the dimensions we live in. It's quite easy to recognize. I always hear people mention time as the fourth dimension, and then it goes on to 12, 11, 12, 13 kind of dimensions. And I was wondering, how do people even come up with these ideas where you can quantify another dimension, because we can't actually observe it or we can't actually experience that? I mean, we understand 1, 2 and 3, but we can't do the rest. And I was wondering if you could give me a bit of an explanation to that, really. How do we kind of get to these other dimensions, and how are they, or where are they perhaps, and that kind of thing?
Okay, so first of all, let's talk about time. So this actually goes back to Einstein, so taking a step back in time. It's a fundamental piece of Einstein's theory that he makes time into this fourth dimension. So already today you've heard me refer to space-time rather than just space. And the difference being that space is the 3 dimensions, as you say, that we live and move in and can think in. And Einstein showed that time can be regarded as on the same footing as those things. And the only difference is that we have no control of our motion through time, unfortunately. But it's not too hard to imagine time as the fourth dimension. You can draw graphs of how something moves with time. So you can put time on the same footing as the others. So then string theory and everything that comes next sort of preserves that. They have Einstein's kind of thought of time as the fourth dimension. But then they start adding these extra spatial dimensions. So it's only ever one time dimension, but you add extra space dimensions. And obviously you say we can't see these dimensions, so where are they? Well, one possibility, and this is what happens in string theory, is that they are, to use a bit of jargon, what we call compactified. Which means they are curled up really, really, really small. So if you can imagine every point in space, I can hold out my fingertip like this, and you imagine at this point in space on my fingertip, there are extra dimensions branching off, but they are curled up into like a sort of tiny circle you could think of. And just the size of those things is so small that no physical object we have, no atom, no measuring device can go into them.
Okay.
And there's a whole branch of mathematics that was kind of developed alongside string theory that talks about the geometry of these compact dimensions.
Okay.
But one way you might detect them, if you do have these extra dimensions, even though you can't put anything solid, anything physical into them, maybe energy could go into them.
Okay.
So you might imagine some sort of particle collision occurs, you have some accelerator, you collide two particles at each other, and at the end of the day, when you look at all the debris that's given off in that collision, you've got less energy than you started with.
Okay.
Right, and energy is conserved, so it can't be destroyed. So where's it gone? Well, maybe some of it's gone into that set of extra dimensions.
Wow, it's pretty amazing. I want to talk to you now about something else which I find interesting as well, is something to do with the multiverse. It's something that's what I'm quite interested in as well. And I've always considered this, that we all live in a place where we think we're limited by our choices. So me doing my degree or you doing your work, I always wonder if somewhere out there's another version of myself, or there's an infinite version of myself where I'm either a king or I don't know, in your position, a theoretical physicist or something. And is there any way of is any kind of evidence to suggest that is actually occurring? Because when people talk about the universe, they always talk about it in perhaps a bubble, and then we have different bubbles of another multiverse, which again is almost infinite again. So we could perhaps, at one point in time, it's getting a bit into the science fiction a bit, but perhaps travel one day to these different kind of interdimensional universes. And just wanted to get your thoughts on that and what you think of that.
Okay, so multiverse ideas crop up a lot when we try and think about theories of the very beginning of the universe.
Okay.
So, I talked about the Big Bang being this primordial fireball explosion and whatever, but you can go back sort of even a step before the explosion and say, what was there before that, or what triggered the explosion?
Yeah.
And this is a really speculative area. It's almost impossible. It's impossible to study this observationally. So it is at the level of ideas and mathematics and people coming up with various models, which at the moment we just have no way of really saying which one's right.
Okay.
But some of those models do give rise to what you call a multiverse. So this idea that there are bubble universes, and perhaps in each of those universes things are slightly different. So in your example, you being a king or something like that. Also maybe the fundamental constants are different.
Okay.
And you can actually show that if some of the fundamental constants, like constants involved in gravity and involved in atomic physics, were slightly different, there might not be humans in, there might not be life in some of these universes.
Different beings, perhaps, or different
beings.
levels of gravity will have different effects on the universe itself.
Yeah, exactly. Maybe some of them are totally sterile. Maybe some of them literally no stars or galaxies ever form, and they're just empty nothingness.
Void, just a huge void of emptiness.
Right, exactly. So, we almost, if a multiverse idea is true, we obviously kind of have to, by definition of our existence, find ourselves in a Goldilocks universe where the constants are right to give rise to beings like ours. Now, your question about could we ever get to another universe, obviously is kind of impossible to answer.
Yeah.
Probably not is the answer. If they are literally completely cut off from ours, then there is probably never a way to get through. But it's all,
it's all theoretical.
It's all theoretical work. Yeah.
One day we might find out. We never know. Another question I wanted to ask you actually was, when the universe was first formed, I always heard that there was a certain amount of matter and antimatter created in the Big Bang. But as we see it, we live in a world where we can see ordinary matter. So, what was it that happened that perhaps shifted the ratios of matter and antimatter?
Good question, and I'm racking my brains here for a minute because it's not something I work on, but my impression is that this is still an unsolved problem.
Okay.
This is the problem of baryogenesis. Why is it that Okay, so as you say, you start off with equal amounts of matter and antimatter, and it only takes a small asymmetry. Something tilts the balance ever so slightly in favour of the matter. And then what happens is most of the matter and the antimatter annihilate in radiation, and what we end up seeing is the small amount of extra ordinary matter that was left over. And we often call ordinary matter baryons.
Okay.
So that's why we call it baryogenesis, what gives rise to genesis birth, the baryons.
Okay.
And this, again, is still an active area of research, and it depends exactly on your theory of inflation and your theory of reheating. So these are two sort of processes that happen in the universe, early universe, to take us from the Big Bang to generating the first particles.
Okay.
And it's still, I think, I can look up models, but it's still not certain.
Oh, okay.
This is what I mean about cosmology still having many unanswered questions.
But I think that's quite amazing, actually, because I sometimes find that when we answer certain questions, whether that be in physics or biology or chemistry, we sometimes find there's more questions from the actual answer that we observed.
Yeah.
So when I a few years ago, I was really interested in the Large Hadron Collider. And I always read books on the Higgs boson and whether it was real or not, and from all the evidence, I read some of John Higgs, some of his work,
Right.
and when they finally discovered it, I think back in Peter Higgs, sorry.
That's right.
There we go. Thank you.
I was thinking for a moment, is there a John Higgs? Is there a John Higgs that
Thanks
I
for
don't know
correcting me.
about? Peter Higgs,
That's
so.
good. And then when they finally discovered it, it was just an amazing discovery. But I always wondered, why did it take so long for them to discover the Higgs? Was it because they didn't have the right detectors for it, or perhaps energies to formulate the Higgs were so big that we couldn't get to them until the Large Hadron Collider was upgraded? Like, what was the main reason for that, if you know at all?
So it is a combination of the things you just mentioned. I mean, the energies available to particle accelerators have just increased enormously within the coming decades. So one could say, it's not quite true, but one of the main goals in building the LHC, the Large Hadron Collider, was to find the Higgs, and they had the accelerator was built deliberately to be able to access the energy range in which we believed the Higgs particle had to exist. So until that point, we just didn't have a facility large enough and energetic enough.
Okay, so say because obviously we've increased our energy output, does that mean might perhaps find some exotic particles that we've never even heard of? So maybe apply them to the standard model, perhaps?
Potentially, yeah. Every time you push up the energy frontier, there's always a possibility of discovering new particles, new states of particles.
Okay.
You do get some indication about whether you're expecting that or not, because what happens if you have a particle that's really high energy, it tends to decay into other things, into lower energy particles.
Yep.
And so if you're sort of sitting there at low energies, you expect, although you don't see the original parent particle itself, you see the daughter particles, the decay products.
Ah, okay.
So if you've had a load of random decay products coming from somewhere, then that might tell you something about this higher energy particle. So you sort of get an indication of what might be around the corner. Okay.
So is any kind of particles that we can predict, and perhaps maybe we know some of the properties other than the particles in the standard model?
I don't think there's anything missing there that we're there's nothing missing from the standard model at the moment. Now that we found the Higgs, that was the last sort of predicted piece that hadn't been sort of detected directly. Okay. There was something, the LHC was a slightly more speculative thing, sort of called beyond the standard model, that the Large Hadron Collider was hoped to find, which was something called supersymmetry. Okay. Which, how to explain this? It's sort of like adding an extra kind of antimatter to your standard model. Now, it's not antimatter, in fact. I don't want to make a confusion here, but it's like saying every particle in the standard model should have a supersymmetric partner, a counterpart, which has
like a positron to an electron.
Sort of. I mean, that is the matter-antimatter counterpart. So it's what we tend to do is we add the letter S to the to the title. So the counterpart of an electron would be the selectron.
Oh,
Selectron. How do you pronounce it? But if you have supersymmetry, then that solves. It makes things work very nicely in particle physics, and it solves various problems. Unfortunately, so far, no evidence for supersymmetry has been found at the Large Hadron Collider. So though it's a beautiful idea, it doesn't seem to, at the moment, it doesn't seem to be correct.
Okay, interesting. Now I was going to ask you, the kind of work you're doing, how did you get into it in terms of, like, you thought, oh, I'm going to study black holes and the formation of galaxies and stuff, and what was the most interesting thing in your field that you really enjoy, and what made you kind of get into it most?
You mean what sort of path did I?
Yeah, so how did you kind of think, okay, I'm going to study, out of everything in physics, why particularly black holes and the evolution of...
Okay, this is a complicated one to explain. I don't actually study black holes most of the time.
Okay.
I guess, so what you do after you finish your physics degree is you apply for a PhD in physics. And the way it works in the UK is that very often supervisors, so senior faculty members, advertise PhD projects.
Okay.
So things that they think are interesting, are interesting questions in the field, and they want to take a student on to try and tackle this question. And that's very useful as a first stepping stone. Because obviously when you come into the field you're kind of naive, and it's like very nice to sit there and say, oh, I want to study X, Y, Z, but you don't really know, you don't have a good overview of what's been done and exactly what the detailed questions are. So your first topic probably gets given to you by a supervisor is the slightly less inspiring answer, although obviously you have some control over which projects you apply for. And that sort of is your incubation period for 3 or 4 years as a PhD student. Okay. But after that, then you've got enough skills and maturity to know exactly how to, hopefully you should know exactly how to choose your own projects. Okay. So I had a PhD in cosmology, and my supervisor guided me towards this idea of working on alternative theories of gravity. Okay. And then now, as an independent researcher, I am able to as you say, have a bit more luxury and sort of look around and say what's interesting, what's going on. So I wrote a paper on gravitational waves last year, based off all the excitement and things that surrounded the direct detection. You got me thinking, what has not been done here.
Okay, that's pretty cool. So what other you mentioned just now that there are other alternative theories to gravity, and maybe you could explain some of the alternative theories?
Yeah, I can try. So one option we've mentioned already is in fact extra dimensions. Yep. So if there are extra dimensions in the universe, then that can alter your theory of gravity. Okay. If gravity is in some sense leaking into those extra dimensions, then that would make it weaker in the 4 dimensions we observe. Okay. So that's one way which changes things on large scales. Yeah. Other possibilities are that there are new fields in the universe. So this is a little bit tricky because I have to explain what I mean by a field. You can think of it almost like adding a new kind of energy to the universe. So there is some how to put this? There's some kind of new fundamental force. Let's put it that way.
It's like an invisible field that we can't really see, kind of enwrapping us all into this.
Yeah, that's it. Okay. So I said there were 4 fundamental forces earlier, and that's the 4 sort of known, tried and trusted and true fundamental forces. But perhaps there are more that we don't know about. So you have one of these extra components that, as you say, sort of pervades all of space-time, and we're all just sort of sitting in a bath of it now. And that potentially can interact with gravity in certain ways. And so there's a lot of work into trying to think about what those new kinds of fields might be. and what they would do.
How would you even go about trying to observe that or trying to quantify that in an experiment? Is there any way of doing that at this moment in time? Or
Yeah, absolutely. So if you have one of these extra fields, what it might do, generically, one of the predictions is that it might enhance the gravitational attraction between two objects.
Okay.
Now, for things like you and me sitting on planet Earth or planets moving in the solar system, there are various. For you and me sitting on Earth, it's too weak, that extra attraction to feel. There are various reasons why you might not be able to detect things in the solar system.
Yep.
But maybe when you look at galaxies in the distant universe moving towards each other, maybe they rush together, maybe they fall towards each other faster because of this extra force due to this new field.
Okay.
So what you would get is what we call enhanced clustering. So basically gravitational structures in the universe would collapse faster than they would in the absence of that new component.
So they almost accelerate quicker when they're kind of merging together, I guess?
Yes. So when we look at the universe on the largest scales, we look at thousands upon thousands of galaxies. They're not just randomly distributed on the sky.
Yeah.
In fact, we see they form a kind of almost like a cobweb kind of structure, a cosmic web.
Yep.
So there's it's like a sponge or like a Swiss cheese with holes in it. And what's actually happening there is that the galaxies are rushing together. They're sort of falling together at the nodes of that web.
Okay.
And the spaces between them sort of form. And it might happen that rushing together, that formation of that web, happens quicker.
It's quite interesting because I looked at some models of one of the filaments they call laniculata. Is it laniculata? So basically they have someone, I can't remember where they did it, but they used a computer to modelize, I don't know, I think it was 40,000 galaxies, and then they found that we live in a cluster called the Super Virgo. Is it Super Virgo?
Yes. So yeah, our nearest big node, if you like, is the Virgo supercluster.
That's the Virgo supercluster, and they found that beyond Virgo supercluster, we're in a huge neighborhood called Laniculata, which is, when they computer-sized it, we could see all the rotations of the galaxies, and we see this huge filament coming in together, and it's just absolutely amazing. And you just think the grand scale of it all, really, like, I always wonder, just because we haven't, found evidence of extraterrestrial life doesn't mean it's not there. And I think with stuff like using the Drake equations to predict, statistically, I genuinely think that it's almost near enough impossible that other beings or extraterrestrial life don't exist when you look at the actual mathematics of it. And even now, with the discovery of the recent 7 planets around the sun, not the sun, a certain star, I can't remember, was it Christ? I can't remember the name of the star, but they found 7 planets in the habitable zone.
Yes.
Which
was it 7 in the habitable zone?
7, I think it was.
They certainly found a number of planets, a fraction were in the habitable zone.
So yeah, I can't remember exactly what it was, but that's still amazing to think we've just discovered a few planets on a star somewhere else in the void that are potentially habitable to other beings. And with certain new telescopes like the James Webb Telescope going into productions, going up into space soon, do you think we'll be able to observe these planets directly more, and maybe perhaps look at the compositions and go more into the kind of climates and see whether they're possible for life to exist?
Absolutely. I mean, this is one of the real growth areas in astronomy for the past 10 years. 10, 15 years ago, we didn't know any planets outside our own solar system. And again, it's technological development. We basically didn't have things sensitive enough to detect these tiny objects.
Yeah.
We think of the planet as being big, but in astronomical terms, they're really tiny.
Speck of dust.
A speck of dust. And then once basically technology became good enough for us to start detecting them, and sometimes we see them directly, and sometimes we have to apply various clever techniques to sort of infer their existence. We started detecting these exoplanets, they're called, planets around other stars, and the numbers just shot up, and now we have, I forget, it was 300 or 400 of them, and we're just finding more and more all the time, and it's a huge growth area. Now, as you say, up until now, the kinds of planets we've been finding are not Earth-like ones. and it's because it's easier, of course, to find bigger things. Not
Yeah.
surprisingly, they're easier to observe directly. They have more massive, so they exert more gravity on what's
Yep.
going on around them. But the problem with very big planets, sometimes with hot Jupiters,
Yep.
is that they tend to have such strong gravity that they would crush any
Just
life
smush
forms
everything, basically.
to pancakes, basically. And also some of them are not in the habitable zone,
Yep.
so they're either too far away from the star, they're too cold, all water would be frozen,
Yep.
or they're too close in. They just get scorched to death.
Oh.
And so the quest at the moment is to find ones like these recent detections in the habitable zone, where, at least based on all the biochemistry we know from Earth, which obviously may not be the complete story, but it's what we've got to go on right now, we think other life forms might be able to exist. And certainly once more and more Earth-like planets are discovered, the sort of next step in that process is then, as you say, to take spectra, so to look at the light from their atmospheres and try and work out what elements are in their atmospheres.
Okay.
And again, that might give us further clues about whether they can support life or not.
How accurate are these measurements exactly to, a realistic sense? If we look at, I don't know, one of the moons in Jupiter, and we can monitor the atmosphere, and looking at light, looking at spectrometry, how accurate can we get with our predictions?
Well, so one this is not an area I work on directly, so I probably couldn't give you the latest up-to-date on planet sizes, but one sort of factoid I do remember is that looking at nearby stars. So stars are not sort of static things. They're very active and dynamic, and they belch and throw out gas and all, and they wobble and things like that. And being told that we could actually measure the motion of the surface of a star that was light years away to about 3 meters.
3 meters.
So the surface of that star, expands or contracts by the order of 3 to 10 meters, and you can actually see that
insane.
kind of pulsation. Which is
amazing.
Distances involved. It's just insane.
I always think to myself, if only I was good at maths, maybe I paid a bit more attention in school in maths, maybe I could have had a better understanding of it. I kind of regret it now. If any of you kids are listening who are quite young, do mathematics, because it does sound a bit boring from my experience, but it is so useful, genuinely.
So useful, and I think it gets more exciting, and it makes more sense. So I've got to say, at GCSE, I didn't particularly like mathematics. It seemed to be this random collection of facts you had to learn for some exam. All these bits of drawing on paper and graph plotting, what is all this about? And it wasn't until I started doing A-level maths things began to fall into place. I think at A-level, is current A-level now, so things change all the time. I felt like I began to get some larger understanding of how all these random factoids fitted together, and I felt I was being handed more tools that I could use. And also the connection to physics, which was always my first love, became more apparent.
It's good to kind of go hand in hand, two sides of the same coin, I know, since you think.
So suddenly I was... we've got a heater that's beeping. Suddenly I was handed tools that I could use to actually answer really cool questions in physics. So, I would say to anyone who's thinking about maths and perhaps not having a great experience at kind of GCSE level, don't let that put you off. I think it gets better.
Definitely. And also I think the more you practice it, the better you get. It's just like any craft, really. If I'd spent at least an extra hour learning to do maths when I was as a kid, then I definitely think I would have done a lot better. But I don't think I really appreciated mathematics until I started doing my master's degree, where we have to learn statistics. So even though I think statistics is a really dry subject, it is so useful. You can look at certain data sets and make interpret data and come to conclusions, which is extremely useful in science, where you need to learn how to do it, really.
And also, to be honest, stats, even in everyday life, a basic knowledge of stats, suddenly you realise how to interpret things that are said sometimes on the news, or sometimes a newspaper will report some factoid like 67% of people think whatever. And whereas previously you might have just read that statement and believe it, now suddenly you've got a set of critical tools where you think, hang on, I'm not sure I trust this. How have you done your stats? And you get kind of smarter rather than just accepting things people tell you.
And I think that's another thing that we should also be doing, is question a lot of things that we're told. Even, again, that can be anyone. I mean, I always tend to tell people to question everything that I'm saying, because only then do you really appreciate, and you can only get the best interpretation of the facts that you have in front of you. I mean, it's all good, and someone, a teacher telling you, a certain thing, which obviously they're more likely to know because obviously they're teaching you something. But it's always good to question them, I think, as well, because then maybe they don't have the full answers, and you have to go and you get more intrigued by these certain questions. And I always think that it is definitely good to question a lot of the things that you've been told.
Absolutely.
So when you're not doing physics, what do you normally do in your spare time?
Well, in my spare time, I very much enjoy sport. I'm a keen hiker, so I've got a group of friends, so I'm out every weekend hiking around. On a day-to-day basis, we hike around rural Oxfordshire, but occasionally we need something a bit more challenging, so we go up some mountains in the Lake District.
Oh, that's awesome. I'm thinking about doing that actually. A couple of years ago I did Snowdon, I did the Mont Blanc.
Oh yeah.
So if you ever...
not near Snowdon.
Oh no! Well, I did Snowdon as well first as a practice run,
and
then
you did Mont Blanc.
Yeah.
Wow.
Mont Blanc. If you enjoy hiking, go to Mont Blanc. Doing the base around Mont Blanc is one of the best experiences I've ever had in my life.
Yeah. We
went in summer and you could literally just drink the water from the mountains just streaming down. It was the most crisp. That's that real Evian water.
Just bottle it and sell it.
Yeah. But no, because we were constantly going up and down valleys. I'd wake up in Chamonix and I could just see the glacier just coming down in the hot summer. It's just still full of ice, just carving the mountains, and just absolutely stunning. So if you get a chance to go. It's one of the best places to go hiking, I think. It's really nice there.
And hiking in general, one of the reasons I love it is gets me away from all my kind of gadgets and whatever.
Oh yeah, definitely just get off the grid.
Get off the grid.
Yeah.
I mean, the nature of the work, but also just all of us today. We spend a lot of time on our phones and our computers. And
definitely.
Don't get me wrong, I'm a tech lover,
yeah,
so I'm
course.
not going to say like go and spend less time on your phone or whatever. But I think just to have that one day a week where I'm literally in a field and there's no laptop and no screen and
no lights, nothing.
Nothing. I enjoy that downtime.
Definitely. I always think to myself that I always wonder if perhaps if we all turn the lights off in when the night came and maybe we could see the stars better, that'd be something quite nice to see. When I was trekking around Mont Blanc, when I was in Italy, because we were on the top peak of the mountains, it went dark and you could just see literally thousands and thousands and thousands of stars, and I sat there and I was like, I have never seen this many stars before. Like, is this even real? Like, it looks like someone just put a projector up there and it's just like press the button and it's just lighting up.
Yeah.
It's just absolutely amazing.
And it's really sad actually. Light pollution is such a problem, especially in a very packed country like the UK. And we don't realise it. People say, oh, there's some stars tonight, because they've lived their life in a city and they see maybe sort of 10, 20 stars in the sky. As you say, you get to a proper dark sky side, out of a city, away from anything, on a mountaintop, and you see a proper night sky. It is beyond imagining.
Of course.
There are so many stars up there. Just seeing the plough or something, it ain't the half of it.
Yeah, of course, definitely not. And from that, it puts into perspective really of how small we really are if you think about it.
Yeah.
I mean, not in a kind of in a horrible way, but in the sense that I always think that people always worry about the things they don't need to worry about. I mean, just to think about, we're on a rock essentially, zooming around a star, which is again zooming around a galaxy, which is that galaxy zooming around other galaxies. To put into perspective, it's just mind-boggling, really. Yeah. And we can see this. We're staring into the sun right now. I mean, it's right there. We don't actually realize how big it really is in the grand scale of things, unless you look at observations and stuff. When I was a kid, I got a telescope, and one of the first things I did was look into the moon, and I could see with such detail and precision all the craters out there, all the marks on there, and it was amazing to think humans have actually been there.
Yeah.
And it's kind of a shame, really. I think that we've stopped sending people to the moon, and obviously I think we can do so much more with that. We can do better tests on the moon. We can look at different sciences. We can, maybe perhaps get some more history on how the Earth and the moon were formed, that kind of thing. And I think it's really interesting doing that kind of thing in physics, really. And maybe perhaps, do kind of run interplanetary kind of missions and stuff. Maybe send people to Mars one day, that kind of thing, which I'm really is amazing.
That would be great. Obviously, it takes a lot of
time planning.
A lot of time and planning and money. Unfortunately,
definitely.
Is always a thing, and it's sad to say in this era of economic crises and budget cuts, science gets hit hard because we are perhaps not something that everyone on the street cares about so much. And don't get me wrong, I absolutely, totally agree that you should prioritise, the NHS and things like that over blue sky research.
Definitely.
Absolutely, 100%. That's what matters to people's lives. But unfortunately, the consequence of that is that some slightly more esoteric bits of science, like sending people to Mars and cosmology, we are the thing that gets hit.
That's true. I always wonder though that do you think going a bit into the political side? I have, just to let everyone know, I have no knowledge on politics whatsoever. So anyone listening, my knowledge is very basic. So I always wonder though, if we did create more jobs for sciences, would that kind of generate more money into it, or perhaps a better understanding of how people look at these things, and perhaps increase our growth in terms of economics? Do you have any ideas or thoughts on that at all?
Well, like you have to say, I'm not a politician or an economist, so it's a slightly tricky area. There is certainly science does have the potential to profoundly affect the economics and industry of a country, particularly some branches of science, perhaps more than others.
Yeah.
So, things like condensed matter physics, laser physics has obviously very strong ties to the electronics industry. Lasers used in reading discs and things like that. So strong ties there. Obviously, on the biomedical side, the production of new drugs and things is a huge industry. So there clearly can be huge economic growth resulting from things like that. For things like stuff I do, cosmology, it's a little bit harder to make the connection, perhaps, but that doesn't mean
we shouldn't
do it. I mean, if we stopped everything that wasn't of direct impact on the economy, I mean, gosh, what a world that would be.
So plain and boring.
Exactly. I mean, mankind has always asked these far-reaching questions for no reason other than the pursuit of knowledge itself.
Definitely. I think that comes in hand again. I think the more knowledge you have on something, the more you can, apply that knowledge and kind of make the world a better place, I think. And like you said, maybe with cosmology, then there might not be such a lot of money to be made in that kind of area. But I definitely think it quenches this thirst of a lot of people have, like, where do we come from? How did we get here? And what is the future? And it's just questions like that I think people are really curious about. And I think curiosity actually is one of the best things that humans have as a trait, especially in sciences, because then we can try and answer those questions. And again, those answers bring up new questions, and then there's maybe a new branch of sciences develops, and you never know. Like one day we could make new technologies out of it. So I think it's always good to be curious, and
Absolutely.
people with curiosity you should not hold it back, and you should just keep going. And if you have that curiosity, I think you do quite well in life.
And there's so much resources available now.
Definitely.
I mean, the internet, for all its ups and downs, is a potentially a wonderful vehicle for knowledge. And I know it gets abused a lot, or filled up with pictures of cats or whatever.
Hey, cats are cool.
but there is also a way there of conveying information to so many people who otherwise wouldn't have access to a decent science library or whatever.
Of course, and I genuinely think the internet is one of the greatest human inventions ever created by man. I mean, literally, I have the world's information on a little tablet that I can take in my pocket, which I think is crazy. If I wanted to pull up information on, I don't know, in something in nutrition, we just type a certain word and type PubMed in or find a database, and boom, I've got all this list of an endless amount of information. But again, I sometimes think that information can be interpreted wrong. I think there's too much misinformation out there as well.
Yeah, you've got to be very savvy.
Definitely.
On the internet.
You shouldn't read everything you should read on Facebook or these weird facts.
Yeah. Always. I mean, as you were saying, know your stats, be curious, challenge what people are telling you, and that goes for the internet as well as in real life. So just because you read it on a website doesn't mean it's true.
Of course.
Find the sources that you respect and trust.
I always find when people say to me, oh, these weird little facts, I don't know, like, I don't know, do you know why the sky is blue? Maybe because there's little beings in there. I'm like, really? Where did you read that? Oh, on Facebook. Oh, you read it on Facebook? Oh, that must be true. Well done. I always kind of like find it quite funny with these little things.
Rayleigh scattering. That's the keyword if anyone's interested. Why the sky is blue? Rayleigh scattering.
There we go. It's quite interesting to be talking to you all these kinds of things. You can give a lot of information to a lot of people. It's really good. You said you play a lot of sports at all. What kind of sports do you play?
So I swim a lot. I have swim coaching.
Oh, awesome.
I used to be a runner. I used to do a lot of running. I would do pretty serious distances, and unfortunately, I had a major accident just over a year ago. To cut a long story short, I was on a dry climbing wall, indoor climbing wall.
Oh, you're a climber?
I wasn't. It was a one-off thing. Went with a friend, and I ruptured this tendon in my body, like one of the strongest tendons that
How did you just climb? You landed awkwardly, perhaps, or what?
I was on this wall and I was stuck. Climbing is a puzzle, and sort of.
I know. I'm a climber.
Right. Okay, you're a climber. Then.
Yep.
So I was stuck, and I was trying to. Good scientist, consider all my options and think about how to move. And I mean, to be fair, I had some prior existing problems. Yeah. But it was just clinging onto that wall for too long, and this pressure just built up my tendon, and it just went bam. Damn. And it was so badly destroyed that they couldn't repair it. So I've got metal in the feet. So now.
Do you, when you go through airports and you go through metal detectors to go off, that's pretty cool.
It is pretty cool.
At the same time, it's not great because you've got like something holding your legs together. It's a little rod.
Oh, I love seeing the look of confusion on the faces when, they come and they sort of pat around my feet and get me to take my shoes off, and there's clearly nothing there.
I am the Terminator. Can mess with people quite well there.
So I'm not running like I used to, but since then I've taken up a lot of different sports, and I've learned that moderation is the key in everything, in sport as well as food and whatever. So I think I'm better off doing a mix of things rather than just
it's really unfortunate. But the thing is, you have to be there's always risk involved in anything, Like I do a lot of weightlifting, and I've been extremely lucky. I've never had any injuries. Again, I think that's from safe practicing of it and the good techniques.
Cross training, I would say to anyone who's out there, if you're doing a sport really seriously, you've got to do your cross training.
Oh, definitely.
Strength training, resistance training,
strength conditioning,
flexibility, whatever
everything.
it is. And that was my fault, my ignorance. I usually put on my shoes and go for a run because it was easy. I never put in the effort to go to the gym and do strength training. Yeah, no,
I think all sports like that, again, they're all come together. You can't really be good at one. You can be good at one sport, but I think it's best to be an overall athlete in that sense. Recently watched a documentary called The World's Fittest People.
Okay.
And it's about these people who do a lot of CrossFit. And people bash CrossFit a lot, and I understand that lifting really heavy things at really different angles. But in the sense of it, they do pretty much all sports combined into one. Okay. And you see these people they're in the competition for 3 days solid, and they're doing some absolute insane exercises. For example, they'll be running 5k, and then after that event, they will be lifting like stones, and then after that event, they will have another event where they'll climb and do courses and stuff like that. And you just watch these people go until their body breaks, and they still keep going. It's just a mental thing, and it's just crazy about how far you can push yourself really physically. And I think a lot of the time it's just a mind thing. If you want something badly enough, I think you can always get it. And I think your body gives up before your mind first. And
you've got to be sensible.
Oh no, of course. I wouldn't say suggest it to everyone, but I'm just saying in the sense that you can do these things, and whether that's beneficial to you or maybe the risk of it is quite high and getting injured. But let's face it, some of those people are extremely fit, And I was watching another documentary called The Berkeley Marathon, where a group of people who get selected by the person who made the event, they have to basically run 5-6 marathons in one go, and just continue doing it with no sleep, nothing. And a lot of the time, 96% of the people who participate fall in that race. And it's quite funny because all the people who were the previous winners are all like physicists and like
Oh,
high academic
really?
achievers. Yeah, it's crazy.
Oh man, maybe my running career isn't over at all.
It's crazy, and there's no course that's plot on in this race. So the guy who comes up with the race, he puts like little clues. So you have to find the little clues first, and then it tells you how to get to the next destination. So you do a lap round once, which is in a clockwise. No, you do 2 laps, which is clockwise, 2 laps anti-clockwise, and you can choose which one you want to be doing. If you're running a little bit low on time, just let us know, and then we can end it whenever you're ready.
I think these people may be coming in here at 4 o'clock. Yeah,
Cool.
so we might just a couple of minutes. To
Yeah, that's fine. We can wrap up in a couple of minutes.
Yeah.
But yeah, and it's just crazy how these people can just do this. And this guy who hadn't slept in 48 hours kept running, and it's just absolutely mental. But then again, he was extremely high achiever and he wanted it.
Yeah.
And his physicist, I think he was a physicist at Harvard or Berkeley. I'm not exactly sure where it was, but amazing stuff. Really interesting.
Physicists doing marathons. There you go.
There you go. That's the end.
Whole new sport.
There we go. I wonder if there's a correlation between that. But yeah. Anyway, I think we're going to wrap it up now. But thank you very much for your time.
Oh, lovely to chat to you.
You too. I just wanted to, do you have a Facebook, Twitter? People can get a hold of you in case they want to talk to you about anything at all?
Yeah, I've got a Twitter handle. It's Tessa_M_Baker.
Okay.
So yeah, feel free to send me any questions or say hi on that.
Cool, great. Well, thank you very much for the podcast, and yeah, thanks.
All right, take care.
Thank you.
Bye.